Welcome back to Science Unlocked. Today, we're diving into a fascinating paper from Nature Physics, Emergence of Phase Coherence in a Magnon Bose Einstein Condensate.
Ooh, that title sounds super technical. But I'm excited. What exactly is a Bose-Einstein Condensate, or BEC, for our listeners?
Great question. Imagine a state of matter where individual particles, like atoms or quasi-particles, lose their individual identities. They all behave as one single quantum wave, a collective entity.
So, like a quantum superorganism? That's wild. And what are magnons in this context? Are they like regular particles?
Not quite regular particles. Magnons are quasi-particles, essentially tiny waves of magnetization that travel through magnetic materials. Think of them as the quantum of spin waves.
Okay, so we have these magnon waves acting as one big quantum wave. What was the big mystery this paper was trying to solve about them?
Well, BECs are known for coherence, meaning their waves are in sync. But directly observing how this coherence spontaneously emerges, how it turns on, has been a huge challenge.
So we knew they were coherent, but not the moment of birth, so to speak? Why was that so hard to see?
Exactly. Previous methods often average measurements over many cycles. This masked the crucial, spontaneous moment when the condensate picked its phase, making it seem like external factors might be influencing it.
So it was like trying to watch a single snowflake form in a blizzard? Too much going on, too many averages. How did these researchers, Maltecosta and his team, overcome that?
They developed a clever phase referenced detection technique. This allowed them to track the condensate's phase in real time, relative to an external signal, and crucially, do it in single-shot measurements.
Single shot, that's the game changer, right? No more averaging away the details. What kind of setup did they use for this?
They use a thin film of yttrium iron garnet, a magnetic material, and a tiny microstrip antenna to excite and detect the magnons. It's quite a precise setup.
IIG film, microstrip antenna, sounds like a tiny, controlled environment. So they pump energy in, create magnons, and then watch what happens?
Precisely. They divided the process into 3 stages: pumping, thermalization, and free evolution. It's like watching a tiny quantum system evolve.
Okay, pumping first. What did they observe when they initially pumped energy in the system to create these magnons?
Initially, the magnons were incoherent, a random phase ensemble. Think of it as a chaotic crowd, all moving in different directions. No global rhythm.
Chaotic crowd, got it? And then, what happens during the thermalization stage as more magnons are introduced?
As the Magnon density increased, they observed a spontaneous transition. The chaotic crowd started to organize, thermalizing into a coherent condensate with a well-defined macroscopic phase.
Wow, so they actually saw the movement system decided on a phase? That's like watching a random group of people suddenly start dancing in perfect sync.
Exactly. And the crucial part is that this initial phase was random in each experiment. It wasn't dictated by the external pump, proving its spontaneous emergence.
That's huge. It confirms a core prediction of BEC theory, right? Spontaneous symmetry breaking. How did they quantify this coherence?
They used a measure called the coherence value, derived from the autocorrelation of the signal. It goes from 0 for noise to 1 for perfect coherence.
And what did that coherence value show? A sudden jump, I imagine, once the BEC formed?
Yes, a clear increase after thermalization, reaching a stable plateau. Even when the signal amplitude decreased later, the coherence remained high, indicating the BEC itself was stable.
So, the BEC doesn't just lose its sync easily, even if the signal gets weaker. That's pretty robust. What are the real-world implications of this discovery?
This direct observation of phase emergence in magnons, which can operate at room temperature, opens doors. It could lead to better Magnon supercurrents and Josephson oscillations.
Magnon supercurrents, like super efficient data transport perhaps, or new types of quantum computing components? The potential for Spintronics and quantum tech seems immense.
Absolutely. Understanding this fundamental aspect of coherence is vital for controlling these quantum systems. It's a significant step forward in our grasp of quantum phenomena.
It's amazing how studying these tiny magnetic waves can unlock such big insights into the quantum world. What a brilliant piece of research.
Indeed. It really highlights the power of precise experimental techniques to confirm long-standing theoretical predictions. A true triumph for condensed matter physics.
And for our understanding of how quantum systems organize themselves, it just makes you wonder what other secrets the quantum realm holds, doesn't it?